All right, we're going to start getting serious about our analysis in rotational dynamics and how and why things move in rotations. And to get there, we'll have to go through a concept called the moment of inertia, which will be defined in a couple of slides. Heads up, the following slides are a little bit formal and dry, but they'll get us something we need to get to. Consider for the moment a thing which is on the end of a rod, and we are exerting a force on the mass at the end of that rod. The rod keeps it from going in a straight line and keeps it moving in a circle. We apply some force, and the rod also has some tension. So this mass has two accelerations. Because it's going in a circle, it has centripetal acceleration. That comes entirely from the tension. That's what changes the direction of the motion. But we might also be accelerating the particle forward. We might be pushing on it, and that would give it increasing speed because it would be an acceleration tangential to the circle, a sub t. And that tangential force will change the speed. From second law, we know the tangential acceleration will be the force over the mass. We also know that because of, let's sketch this the way we did before. If we have that it's tracked out some arc length s over some radius r, so we had theta equals s over r, then s equals r theta, which means that delta s over delta t is r times delta theta over delta t, or v, the tangential velocity, would be r omega. And then likewise, delta v over delta t is going to be r delta omega over delta t, and that's going to be our tangential acceleration a, and we see that's equal to r alpha. So we have alpha equals a over r. And that's what gets us from that step to that step. We also know, of course, that the torque exerted by this force would be Rf. So if we put these things together, we end up with alpha is tau over mr squared. So if we think of this as the analogy of force, then this must be the analogy to m. This must be, if this is the impetitive thing, this is the inertia bit. So this is what we're going to focus on. For a single point mass, a distance r from its point of rotation. If we have 3 points on a rigid object, and that is fixed to rotate around this point, and we pull on all of them with their own little forces, then they'll each exert torques, which causes there to be a net torque, which would cause the thing to accelerate in an angular sense. The torque for each of these particles would be its mass times its distance from the axis squared, but times the common acceleration. So the net torque, of course, just means add the 3 up. So we'll have m1 r1 squared alpha plus m2 r2 squared alpha plus m3 r3 square alpha, plus if there were more particles, we keep doing that. We factor out the common alpha, and we find that the net torque is alpha times the sum of mr squared for each particle. So again, this must be the thing acting like an inertia term. That constant of proportionality, the thing between the torque and the angular acceleration, is called the moment of inertia, which is the old school way of saying it, or in more modern parlance, the rotational inertia. It is symbolized by I and measured in units of kilogram per meter square. Sorry, kilogram times meter squared, not per meter square. As a really quick aside note, this is actually, I think, supposed to really be the Greek letter iota, which is visually identical to the Roman letter I. And I think it's supposed to be iota to keep track of the idea that rotational things are Greek letters and translational things are Latin letters. Nobody in the whole world does that. We all write it as I, we all think of it as I, but it kind of breaks that useful little parallel. So I just wanted to point that out there. For a single mass point particle m located distance r from the axis of rotation, the rotational inertia is mr squared. And that's one they do kind of expect you to know. It's easy, and it is on the equation sheet, but you want to feel pretty comfortable with it, that if the thing is small enough to be considered point-like, then its inertia is mr squared. And if there are multiple point particles, and we add up their individual inertias to get the total inertia, probably should be careful if they're point particles around the same axis. It gets a little weirder if they're around different axes, and in fact can be quite a disaster, but we won't worry about that in this context. If the object's not a point particle, well, then things get more complicated, and we're going to come back to that in a little bit. So 3 heavy marbles are glued securely to a lightweight disk as shown. Circle in blue the letter or letters of the disk or disks with the greatest inertia. rotational inertia, and circle in red the letters of the disks with the least rotational inertia. These are all collections of point particles. Since the disk is lightweight, it means it doesn't itself have any inertia, so we don't worry about it. And we'll treat the marbles as if they were point-like. So if we look at case 1, we have a thing which is a distance r away. So we have mr squared for that one. And then we would have this one, which is also mr squared. And we would have this one, which is also mr squared. So all told, all of those end up adding up to a total rotational inertia, which is 3mr squared. In case B, all of these guys are at radii that is essentially 0. And so we get something like, almost at least, m0 squared plus m0 squared plus m0 squared, or essentially 0, approximately. There's not quite 0 radius, so it's not quite, but it's obviously much, much, much smaller. All right, here we have mr squared. We're rotating around that point, so we get m times 0 squared. And then we have this one, and that's m times r squared. So all told, these equal 2mr squared. And then the interesting one, if this is our blue one, we have m but times 2r quantity squared. And if I take this one in green, it's m times 1r squared. And if we take this one, the one in red, well, the one in red doesn't actually contribute. So we have m0 squared. And adding all of those up, we have 4mr squared plus mr squared, or 5mr squared. So this is the case with the most, and this is the case with the least. About which axis is the rotational inertia greater? The bars themselves are massless. How is this thing actually moving? Well, if we look at that, this is the axis, then everything's exerting a circle around that. So if you sort of imagine coming out of the plane, it does something like that. Same circle. And of course, hardly any spin. Remember, these circles are meant to be sort of in the plane. Sort of imagine out of the board or of the page. If we go over to object 2 or case 2, well, the red one has no radius still. And the blue one is now tracking out a circle like this. And the green one is tracking out a circle like this. It's in the plane of the page. So if we consider the rotational inertias, in both cases, m1 exerts it contributes not at all to inertia. All right, it's m times 0 squared, 0 contribution. In this case, the contribution of this one is the same because the distance is 10 in both cases. And so it doesn't, for the comparison, it doesn't help us at all. They both gain the same amount of inertia from that one. But when we look at m3, this has a radius of only 10, and this has a radius of 14. So m14 squared is going to be more than m10 squared, and so axis B is going to have a greater inertia. Notice we haven't changed the object, and that's really important here. We have to pick the point of rotation. If you say, well, what is the rotational inertia of this thing? The question is actually meaningless. We have to say about what point. Traditionally, we pick the actual point of rotation, but you could pick anywhere you want. You have to stick to what was specified. That's all. All right, consider a uniform disk of mass m and radius r, and a thin hoop with the same mass and radius. Assume the thickness of the hoop is much less than the radius, so it's very, very thin, which will have a larger rotational inertia about an axis through the center and perpendicular to the plane of the object. So if we consider case 1 is the hoop, and we're talking about this axis. And then case 2 is the solid cylinder, or disk, I guess. Same kind of axis. But now we're solid. All right. Well, if we look at this, some of the mass that's here has been sort of spread out, or inward really, and therefore contributes less. So on average, the mass is closer in this case. So on average, R is less. Here, the R is just the R of the hoop, but here the R is less. In this case, some of the R's have less. So it turns out that the hoop will have greater inertia. All right, that leads us to, if an object is not point-like, we need calculus to compute the moment of inertia. And you won't be asked to do that. That's not a topic for AP1. It is a topic for APC, so if you end up taking that class, you'll get to do this formally and on your own. But there are several highly symmetric shapes whose rotational inertia you can use. This is a chart that's found in your textbook. It's found in every textbook. It's not a kind of thing that the College Board expects you to know offhand, but it is sort of useful to know it's out there. If they need you to compute things with rotational inertias, they will generally give them to you. They don't ask you to know any of them except the point mass one, mr squared. Looking at this, we see some patterns. Our hoop has mr squared and our cylinder 1/2 mr squared. So we see that confirms what we had before. The factor of half is semi-easy to understand because we can think of it as sort of the average between having all of the mass at radius r and all of the mass at the center, and we just average those two cases, and we get a 1/2 mr squared. That's fuzzy and not really valid, but it's not a bad way to remember it. For spheres, we get factors of either 2/3 or 2/5, and those really just fall out of the geometry. It's really hard to say why those happen. I've never come up with a way that says this is why it makes sense, but do notice that again the solid object is less than its equivalent hollow object because again some of the mass is towards the center and so therefore it doesn't contribute as much. Over here we have more flat objects, and it's probably worth again noticing that if you try and rotate a rod about its center, then you only get a 1/12, very little. But if you go about one end, you get 1/3 or 4 times as much inertia. The plane is not that big a deal. Doesn't seem to show up that much. It doesn't seem to make a lot of sense. Notice you still get the 12ths and thirds because it's functionally equivalent to about the center of a rod or the end of a rod. All right, these hoops and disks each have the same mass m, but the bigger ones have twice the radius of the smaller ones. Circle in blue the objects with the greatest rotational inertia, and in red the objects with the least. All right, so we know that in general, the hoops will have more than the disks of the same size. So we know that this is more than that, and this is more than that in terms of rotational inertia. But we also know that it scales with the radius squared. So if they all have the same mass, right, if, as they say here, it's the same mass m, then the larger one will also have a larger thing. So we know that this is more than this. Well, if this is more, and that this is more than this. So if this is more than this, and it's more than this, and transitively, since B is more than D, then A is more than B and also more than D. And we know A is separately more than C, so A must be the most. In exactly analogous reasoning, we know that this disk is less than that hoop. We also know that this disk is less than that disk. And so we should end up with that as our least.